Okay, good afternoon, everyone. Thanks for coming to our statistics CRM seminar this afternoon. It's my great pleasure to introduce to you Dr. Stanislav Volgushev from Department of Statistical Science at University of Toronto and also Department of Mathematical and Computational Science at University of Toronto at Mississauga. Stanislav main research, he joined, I was just asking him, he joined U of T in 2016. His main research area, in a broad sense, it covers data science, probability, and theoretical statistic. If you want to know more about the details of his research, please visit his website. A fascinating website, I would say. He is editorial activities, a couple of top statistical journals, Electronic Journal of Statistics, Canadian Journal of Statistics, Scandinavian Journal of Statistics, and he used to be also associate editor for Bernoulli between 2016 to 2018. Today he's going to tell us about graphical structural learning for extremes. Stanislav, floor is yours. Thank you.
Okay, yeah, so thank you for the very nice introduction, and also thank you for the invitation to give this presentation. It's both an honor and a pleasure to be presenting, and also thanks to everybody who made it despite the snow in Montreal. So, and the first and most important thing is that this presentation is going to be based on joint work with two really wonderful colleagues. So one of them is Sebastian Engelke, who is at the University of Geneva. And the other is Michaela Lancet, who is actually a PhD student in our department. And Michael will be graduating this year. And so part of what I'm going to present is part of his thesis, but his thesis contains much more. And he is also from the French-speaking part of Canada, and he is looking for faculty positions in the French-speaking part of Canada. So allow me to just start this with a shameless advertisement for Mikhail, because he's really a wonderful scientist, but also just a really nice person, and I'm sure he'll be a wonderful colleague. Okay, and so my talk will be about graphical structure learning for extremes, and so I would like to start by introducing what I mean by each of the words on the title. And so the first word that I'm going to discuss is extremes. Okay, so here's one slide sort of on a brief introduction to extreme value theory. Okay, and specifically the type of distributions that I'm going to be concerned with are multivariate Pareto distributions, and they are linked to the notion of threshold exceedances. So the motivation for considering this type of distribution assumes that you have random vectors x1 to xd, and the entries of those vectors could denote something like a temperature at different locations on a given day, or they could denote the gains or loss in a stock on a given day, and so on. And what we are interested in is saying something about the distribution of x if you have additional side information, namely that at least one of the entries of this vector is large in the sense that it exceeds a high quantile. And if you think of the stock market example, for instance, if you know that one of the stocks had a very large loss, then it might be that it was a very large loss because it was a bad day for that company, but it might be that it was a very large loss because of the general economic situation and because there is a financial crisis going on. And then we might expect that the dependence structure in those random vectors where at least one component is large is different from the dependence structure in the bulk of the data. And extreme value theory broadly tries to say something about the dependence structure, given that our observations are extreme in a certain sense. Okay, and in this particular talk, extreme will mean that at least one component of the random vector is large. And this is also known as peaks over threshold modeling. So this is a popular approach in risk modeling and in modeling weather extremes and climate extremes and so on. Okay, and so from a more mathematical standpoint, what we are considering here is the following assumptions. So we take our random vector x, and then we transform its marginals by the marginal CDFs to be uniform. And we condition on the fact that at least one observation or at least one component of the random vector exceeds a 1 minus q quantile, where q will tend to 0, so 1 minus q will be close to 1. Okay, so this statement here is stating that at least one component of the vector is large relative to its usual distribution. And then we assume that if you look at the joint distribution of all the other components and condition on this event, that as the quantile level goes higher and higher, this conditional distribution stabilizes in the sense that it converges in law to the distribution of some random vector y. Okay, and so that's one of a typical type of basic assumptions in extreme values theory. Okay, and so because of this conditioning event over here, essentially what that implies is that this random vector y will not be a random vector that is supported on all of Rd, but rather it will be a random vector that will be supported on this shape, on this L-shaped space down here. Okay, so in D2, this L-shaped space looks somewhat like this. So we take out the corner at 1, 1. Okay, and so this is not a product space, and that will play an important role later. And the notation that I'm going to use for this type of convergence is I will say that the random vector x is in the domain of attraction of the random vector y. Okay, and so broadly speaking, what we are hoping is that the distribution of the random vector y will be informative about the distribution of the random vector x, conditioning on the fact that it is relatively extreme. Okay, and so we are looking for reasonable models for this type of distributions in this type of settings. Okay, now a couple of additional comments on that. So first of all, because I standardized the random vector x with its marginal distributions, this means that the information that we have here is really about the dependent structure of the random vector x. So we kind of discard the marginal information at this point, and what we are really interested in is a margin-free dependent structure. Okay, so this is of course very similar to the concept of copulas, and also this is of course related to notions of extreme value copulas and related things. Okay, the second comment is that the distributions that can arise as limits up there are typically called multivariate Pareto distributions, and it will become clear in a couple of minutes why this is a reasonable name. Now, a couple of words on their properties. So first of all, it's relatively straightforward to show that if a random vector y arises as a limit as above, then it must satisfy a property that's called homogeneity. Okay, and so what that means that if we take a set A that is a subset of this L-shaped space, and then we blow up every point in the set A by a number t that's greater than 1, then the probability that y lands in t times A is 1 over t times the probability that 1 lands in A. Okay, that's a relatively straightforward consequence of the limit above. So the limits that can possibly arise have this homogeneity property, and essentially what that means is that in a sense this is a lower dimensional distribution. Okay, so it's not completely general, but once we fix certain aspects of it, we can obtain other aspects by through this homogeneity property. Okay, so those distributions are not completely general. It is a restricted class of distributions. And then one can also show that any limit that arises as above will satisfy this kind of marginal standardization. So the probability that any component of that random vector exceeds the value 1, all of those probabilities must be equal. And conversely, one can actually show that if those two properties hold, so homogeneity plus this kind of marginal property, then those together uniquely characterize all possible limits. So any distribution on L that is homogeneous and which satisfies this equation down here is a possible limit that we can obtain up there. Okay, so we see that although this class is restricted relative to general distributions on L, it's still fairly general and it's still completely non-parametric. Okay, so in contrast to the one-dimensional case, this is not a parametric class of distributions. This is actually a fairly general class of distributions. Now, a brief comment on why those are called multivariate Pareto distributions. So although the marginals of this random vector x are not themselves Pareto, there is a connection to the standard Pareto distribution, which arises if we take, first of all, we take the random vector ym, which we obtain from y by conditioning that the mth component of y is greater than 1. Okay, so we assume that one component is greater than 1, and then we obtain the distribution of a random vector ym. And now by homogeneity, the mth component of this vector ym will in fact follow a standard Pareto distribution. Okay, and so that explains the name multivariate Pareto distribution, because certain conditional distributions derived from the marginals of this vector are actually standard Pareto. Okay, and so those random variables ym, those random vectors ym, will also play an important role in going forward. Okay, and so in general, sort of the summary of the first two slides is that those multivariate Pareto distributions are motivated through this limiting relation, and this motivation makes them a very natural class of models for modeling observations with extremes. Okay, and that's also essentially their importance. Now, throughout the remaining part of my talk, I will make a simplifying technical assumption, which will make stating some of the results that are going to follow a bit easier, but I'd like to mention that this assumption can be dropped. Okay, and essentially what I'm going to assume is that those random vectors y do not put mass on lower dimensional subspaces that contain the x's. Okay, so it's this condition down here. So in the two-dimensional case, it means that there's no mass on the axis, and in higher dimension, it means that there's no mass on the lower dimensional subspaces that touch the axis. And if that's the case, then actually by homogeneity, the distribution of y on this L-shaped space is completely determined by the distribution of any ym. Okay, if we drop this assumption, that's not true anymore, and things get a bit more complicated. But as I mentioned, some of the results that I'll state going forwards remain true without this assumption. Okay, and so that was the introduction of what I mean by extreme value theory. And now next, let me talk about what I mean by graphical structure. So, and for that, I'd like to sort of introduce or remind everybody who has seen this of the notion of a probabilistic graphical model for a random vector x. Okay, so in general, if you have a random vector x on Rd, then we can identify the entries of that vector with vertices on a graph. And then the presence or absence of edges in that graph will contain certain information about the conditional dependence structure or about factorization of densities of this random vector x. And there's a couple of popular ways to do that. And the first two are related to notions of conditional independence. And the first one is the so-called pairwise Markov property. So what the pairwise Markov property is saying that if for a graph, an edge is not part of that graph. So for instance, if there's no edge between v and w, then the random variable xv will be independent of xw, conditioning on all the other random variables. Okay, so here's a simple example. If you look at this graph up here, then the pairwise Markov property would essentially imply two conditional independence relations. So there's no edge between x1 and x3, which means that x1 and x3 would be conditionally independent given everything else, so x2 and x4. Okay, and similarly, there's no edge between x1 and x4. So that's the second conditional independence relation. Okay, so that's a pairwise Markov property. Now there's also a global Markov property, which is stronger. And that is stating that if you take subsets of vertices, A, B, and C, and if the set A will separate the set B from the set C, then the random vector containing entries in B will be independent, conditionally independent of the random vector containing entries in C, once we condition on the vector on the entries in A. Okay, so in the example on the right, this would give us two additional conditional independence relations. Okay, so for instance, we see that if we take x2 out from that graph, then there will be no connection between x1 and x3. So x1 will be independent of x3, just conditioning on x2. Okay, and so that's an additional property in addition to the pairwise Markov property. And similarly for the conditional dependence between x1 and x4. Okay, so in general, the global Markov property will give us more conditional independence relations than the pairwise Markov property, which means that it's a stronger property. And finally, a related notion is linked to density factorizations. And in terms of densities, we say that X has a density that factorizes with respect to a graph G if we can write the joint density of the random vector X as a product of lower dimensional functions, and each of those functions now only depends on a subset of variables at once, and those subsets of variables are the subsets of all cliques in the graph. Okay, so cliques are completely connected subsets. Okay, so in the example of the graph up here, essentially there's two cliques. The first clique is x1 and x2. So that's the first function, and the second clique is x2, x3, x4. So that's the second function. Okay, and this can also be generalized to other graphs. And finally, there's a very famous result called the Hammersley-Clifford theorem, which links all of those properties together. And it is stating that if X has a positive density with respect to a product measure, so that could be Lebesgue measure, or it could be counting measure, for instance, then all of the above properties are actually equivalent. Okay, so in that case, pairwise Markov property implies a stronger global Markov property, and that's also equivalent to density factorization. And the utility of graphical models is now twofold. First of all, because of this density factorization, graphical models allow for more efficient simulation from high dimensional distributions. Okay, because we only need to evaluate potentially lower dimensional integrals or lower dimensional densities. And the second utility is that by looking at the graph, we can gain some understanding about the underlying dependent structure of this random vector X. Okay, so of course, in general, the dependent structure of a random vector X in dimension D can be very complex. But by looking at the corresponding graph, at least we get some sense about conditional independence relations, and we might get some sense about which variables are really dependent on each other and which variables are independent once we take into account all the other information. So this is also a very useful tool for exploratory data analysis and for understanding complex dependence relationships in general random vectors. Okay, so that is graphical models, and this notion has nothing to do with extreme value distributions. So what I'd like to do in this talk is to specialize this to the setting of extreme value distributions or multivariate Pareto distributions, and also talk about how we can actually learn this graph from data. Okay, so and one thing that has prevented people from coming up with suitable notions of graphical models for multivariate Pareto distributions is the fact that the classical notion of conditional independence actually doesn't make a lot of sense for distributions that are defined on a space which is not a product space, right? So recall that those multivariate Pareto distributions are defined on this L-shaped space. And actually the classical notion of conditional independence doesn't really make sense on a space that's not a product space. Okay, so the thing that we would need to do if you want to come up with reasonable probabilistic graphical models for multivariate Pareto distributions is to come up with a suitable notion of conditional independence. And this was done by Sebastian and one of his co-authors, Adrian Hitz, in a very nice GRSSB discussion paper in 2020, where essentially they proved that a useful notion of conditional independence for multivariate Pareto distributions is defined through classical conditional independence for those vectors ym for all m. Okay, so once we condition our vector y on the space L, on taking on one component being larger than 1, then ym is now actually supported on a product space. And for this, it makes sense to talk about conditional independence. And what they proved is that this is a useful way of talking about conditional independence. And they also provided a Hammersley-Clifford type of theorem linking this to things like density factorization and related things. Okay, and so this was work that was done by Sebastian Engelke and Adrian Hitz, and they essentially assumed that the multivariate Pareto distribution has positive densities. Now, what I'm going to do, at least for part of this talk, is I'm going to think about a slightly more general setting where I don't assume the existence of densities. And what that will imply is that I need to be careful about the notion of graphical models that I choose. And throughout this talk, whenever I talk about graphical models without further specification, I will mean graphical models in the sense of global Markov property relative to a graph. Okay, and if densities exist and if they are positive everywhere, then this is equivalent to the other notions. And the other and much more important thing about this talk is that Sebastian and Adrio essentially assume that the underlying graph is known. Okay, so their paper is really a modeling and kind of probabilistic paper that tells us if we know the graph, then how can we construct a multivariate Pareto distribution on that graph. Now, what I would like to do throughout this talk is to kind of reverse that question, which means that I would like to learn the graph from a sample. Okay, so what I will assume is that we are given a sample x1 to xn from a random vector x. That random vector x is in the domain of attraction of a multivariate Pareto distribution y. And I'm interested in learning the graphical structure of y. Okay, so we don't even have direct observations from y. We only have observations from x, which is in the domain of attraction of y. But that's actually the practically relevant setting in extreme value theory, right? Because we have observations, then we take all those observations that are extreme in a certain sense, and then we approximate their distribution by a multivariate Pareto distribution. Okay, and so that's what I would like to try to mimic in the methodology and also in the theory in terms of going forward. And I will essentially talk about two types of graphical learning procedures. So one of them is for completely general multivariate Pareto distributions, but for a very special type of graph, namely for trees. And the second one is going to be for a very special parametric class of multivariate Pareto distributions, namely Hüsler-Reiss distributions. But I will allow for completely arbitrary graphs as long as the graphs are connected. Okay, so in the sense, those are kind of the two extreme settings, either very simple graph but general distributions, or very special distributions but very general graphs. And this actually is very much in parallel to the developments that have taken place in the non-extreme world, because there it is well known that if you have a multivariate Gaussian distribution, then graphical modeling amounts to estimating the sparsity pattern of the corresponding precision matrix. Whereas if we have graphical models on trees, then if you put, then there are ways to learn those trees in a more or less non-parametric fashion. But it will turn out that in the world of extremes, some things are nicer and simpler than in the classical setting because of this homogeneity property. All right, and so first, let me talk about the special case when the underlying graph is a tree. Okay, and so just to make sure we're on the same page, so a tree is essentially a graph that doesn't have cycles, which means that if you have a couple of points, then a tree might be something like this here, for instance. Okay, but we are not allowing cycles, so that's a tree. Okay, and it is a relatively special type of graph. Okay, now for that, a bit of preliminaries. And the first thing that I'd like to define to make things more concrete is the concept of a minimal spanning tree. Okay, so in general, assume that we are given a collection of vertices V, and we are given a collection of distances on all possible connections between all the vertices. So in the example on the left, for instance, we could have we have three distances between y3, y1, y2, y1, and y3, y2. So let's say that the distances are 3, 2, and 1. Okay, and then we define the notion of a minimal spanning tree, which has to satisfy two properties. First of all, it's a tree. Second, it connects all vertices in the graph. And third, if you sum the distances on the edges of the tree, then that has to be the minimal possible distance. Okay, so in the example of this graph, essentially the tree, the minimal spanning tree would be the tree on the right. Okay, because that satisfies the sum of distances on the corresponding edges. Okay, so that's a very classical type of notion. One can show that the minimal spanning tree is unique if all the distances are distinct. And there's also very efficient computational algorithms for computing minimal spanning tree, even if the dimension is fairly large. And the classical result is essentially saying that if we have a probabilistic graphical model on a tree, then for specific parametric distributions or for distributions with densities, if we use specific ways of measuring distances between entries of those random vectors, then we can recover the true underlying tree from the minimal spanning tree with respect to those distances. Okay, and so classically, this was done for parametric distributions by Cho and Liu in 1968, and there's a notion of Cho and Liu tree, which is a very classical thing in graphical modeling. And then for non-parametric estimation of mutual information, there's a somewhat more recent paper by Han Liu and Wasserman and a couple of people from Carnegie Mellon. Okay, but what I will show in going forward is that things are actually nicer and simpler if you're in the class of multivariate Pareto distributions. And here's the first result from a paper with Sebastian, which goes as follows. Assume that Y is a multivariate Pareto distribution. That's a extremal graphical model on a tree. And assume that it's not degenerate in the sense that no two components of the random vector are equal with probability 1. Okay, so there's no degeneracy in the tree. Then on a population level, we can recover the underlying tree as a minimal spanning tree corresponding to several types of summary statistics. And the first summary statistic is related to something that's essentially very classical in extreme value theory. It's called the extremal coefficient. Okay, so that's a classical notion in extreme value theory. And one way to look at that is, if you remember this L-shaped space L on which Y was concentrated, then essentially it is the mass in this rectangle here. Okay, so we can imagine if there's a lot of mass up here, then the two entries of Y will tend to be large simultaneously, which means that there's a strong dependence. And if there's not a lot of mass up here, then they will tend to be more independent. Okay, so in a sense, this measures dependence. And what we proved in the paper is that we can recover the underlying tree T as a minimal spanning tree with respect to minus log of the corresponding chi-ij's. Okay, so that's one. And this is a very simple summary statistic. It's completely non-parametric. We don't require densities. We don't require specific parametric distributions. It's enough that we have a multivariate Pareto distribution. And we already can recover the tree from a very simple summary statistic. And the second result, which was actually the first result that we proved, is that it can also be recovered from a so-called variogram matrix. And this variogram matrix is essentially related to Hüsler-Reiss distributions. And it appears very naturally in there, but it turns out that it also appears very naturally when we look at multivariate Pareto distributions. So that's the second result. And so we introduced this here in full generality in our paper. And in order for this to exist, we need certain technical assumptions. So this chi coefficient always exists. This guy here exists under additional assumptions, but as I will show later, if it exists, then it's a much better way to recover the tree on a sample level. All right. So the first insight is that for extreme value distributions, we can actually recover underlying trees in a very simple and a very efficient way without the need for density estimation or for parametric assumptions. Now, that's on population level. So of course, the next thing that we would wonder about as statisticians is how do we do things on sample level? And the probably most classical and simple way in statistics is, of course, a plug-in principle, right? So we have a result on population level. Now we plug in everything that's unknown that we estimate based on our sample. And then we try to prove that this actually works. Okay, so more specifically, let's now assume that we have a sample x1 to xn from x that is in the domain of attraction of y. And recall that the link between y and x was provided through a limiting relation where I assumed that we standardize x by its marginal distributions. Okay, now of course in practice those marginal distributions are unknown. So in practice we replace the unknown marginal distributions by the corresponding empirical CDFs, very much in the same way that we would do things for empirical copulas. And we take care of the fact that we are only in the domain of attraction by only considering large observations of this vector x in the sense that at least one of their components is large. And putting those two ideas together, it's straightforward to derive plug-in estimators of the extremal coefficients. which is essentially very classical, and also of the empirical extremal variogram, which, after staring at the limiting relation between x and y and on the definition of gamma ij, becomes very natural. Okay, so I won't go into details here, but essentially, if you look at those formulas, and those two are probably the most canonical things that one could do as a plugin estimator. Okay, now a comment on this here. So because x is only in the domain of attraction of y, and because we are only using large observations, we need a way to quantify what a large observation is. And a classical way to do that in extreme value theory is to say that we only take the k largest observations from our sample n. Okay, so this k here that appears in both of the definitions up there is essentially a threshold parameter, and the interpretation is that k divided by n is approximately this this q that was going to 0 in the limiting relation between x and y. Okay, so the idea is that we pick k relatively small relative to n, and then we hope that this limiting relation is sufficiently close to being true. And so, for instance, if you look at the definition of the extremal variogram here, this condition here is stating that we only pick observations xt, where the m's component is among the k largest in the entire sample. Okay, so that's a very natural thing to define what a large observation is. And one thing that I'd like to briefly mention is that in extreme value theory, we typically assume k over n goes to 0, but it will turn out that for some of the results that follow, this is not necessary. Okay, so now we have our plugin estimators, and now we will estimate our tree of the multivariate Pareto distribution y through the minimal spanning tree, which is constructed based on those estimators. Okay, that's our estimator. The next question is, under what conditions does it actually consistently recover the tree structure? And in order to answer that question, and I'd also like to answer this question in a setting where the dimension of the tree is allowed to grow with a sample size. Okay, and in order to do that, what we need is a bit more than just consistency of those estimators. What we need is some kind of concentration bounds for those estimators. Okay, or uniform consistency over a growing number, over a growing dimension. And for chi, this is relatively straightforward to derive from existing results. As far as I see, as we could see, it didn't exist so far, but it wasn't too difficult to derive. And for gamma, it turned out to be an extremely technical and difficult task. But Mikhail succeeded in doing that in his PhD thesis. Okay, and so this is the type of result that we would get. Now, this slide looks fairly technical, so let me just walk you through the highlights here. Okay, so first of all, we need 3 conditions on the underlying data generation process. The first condition up here is essentially taking the limiting relation that we had for describing x through y and requiring that this limiting relation holds with a certain rate. Okay, so there we just said, essentially we said that this stuff is supposed to converge to this here. Okay, now to quantify the rate of convergence, we need some bounds on how quickly this convergence takes place. And the second assumption that we need to make here is that this convergence is uniform over certain sets. Okay, now the one thing that I'd like to say here is that although this looks relatively unwieldy, it is actually it relates back to assumptions that are called second order assumptions in extreme value theory. And it can be shown that this is equivalent to standard second order assumptions on things like the stable tail dependence function. Okay, so for people who have worked with extreme value theory, this is essentially a fairly standard assumption in asymptotic analysis in extreme value theory. And the second 2 conditions essentially are conditions that quantify how much mass the 2-dimensional subvectors of y can put near the axis. Okay, so both of those conditions essentially quantify in slightly different ways how much mass there can be near the axis. And those are all the assumptions that we need. So under those 3 assumptions, it can be shown that if you look at all possible variogram matrices over all possible values of M. Okay, so those guys are now sort of M d by d matrices. And then we look at the maximal possible deviation between any two entries of the estimator minus the truth. Then the probability that that exceeds a threshold of this form here decays exponentially in lambda. Okay, that's the technical result. Now, a couple more explanations here. So first of all, there's two pieces in here. And one piece is this piece here, which will look familiar to people who have worked with concentration inequalities in the non-extreme case. So this is the part that is due to the stochastic error. Okay, this is the part that is due to the fact that gamma hat is based on data. And essentially, that part behaves like 1 over square root k, which is the natural variance that you would get if you take an average of independent things, of k independent things. Okay, so it's k not n because we only use k observations instead of n observations. So this part is natural. And then the second part, which is this one here, is essentially a bound on the bias of the expected value of the empirical extremal variogram that corresponds to x minus the empirical variogram that corresponds to y. Okay, and that part is sort of due to this approximation domain of attraction condition. So that's something that's specific to extreme value theory. So this is kind of the bias part, and this is kind of the variance part. And now what we see here is that the dependence on d is d to the 3, but at the same time, we have e to the minus c times lambda square. So after a bit of computations, for instance, if the bias wasn't there, then we can see that we still will get something that converges to 0 if k grows exponentially in d. Okay, so this is a fairly strong result, and it's actually similar to classical results for bounded random variables. And now that we have this concentration result, we can come up with guarantees that will tell us under what conditions we will be able to recover the true underlying tree based on data. Okay, and so that is the next result. Okay, and so essentially it takes the form of a bound on the probability that our estimated tree based on the minimal spanning tree based on gamma is not equal to the true tree. Okay, so again, this looks a bit technical, but each term in here has a nice interpretation. Okay, so first of all, this b and k here is again a bound on the bias term when we approximate the variogram of y through something that's related to x. And this mu gamma quantity here essentially can be interpreted as a minimal separation condition, in the sense that this mu gamma provides us a lower bound for the sum of distances on the minimal spanning tree versus the sum of distances on any other tree. Okay, so what one can show is that the sum of distances on the second longest tree minus the sum of distances on the shortest tree is lower bounded by this mu gamma. Okay, and it's very natural to expect that if mu gamma is small, which means that if the second largest tree has a similar length to the smallest trees, then it's easy to confuse those trees based on samples because we make errors in estimation. So small mu gamma makes the problem hard, and large mu gamma makes the problem easier because then there's more separation between the true tree and the next best tree. Okay, and so that's also something that we see in this bound here. And the other thing that we see is that again, this bound scales as d cube, but it's where d is the dimension, but at the same time, it's exponential in k. Okay, so now we can play the game of trying to fix certain things in this bound and then see what that will tell us. Okay, and for instance, if we fix the model dimension d, and if we fix the model, then we get consistent recovery of the tree under fairly mild addition assumptions on k. And one thing that's interesting here is that in contrast to classical extreme value theory, we do not require that k over n goes to 0. It is sufficient that k over n goes to a number that's sufficiently small. Okay, so that was an interesting discovery for us. And if we want to optimize this probability of recovering the tree over the choice of k, then it also turns out that there's a different balance between the bias and variance than we would get if you choose k to optimize estimation. Okay, and then another thing is that if you assume that the minimal separation between trees is fixed, but we allow the dimension to increase, then we can get consistent recovery when the dimension increases almost exponentially in k. Okay, so there's a log n to the 8 factor here that kind of is a bit of a technical thing that comes from the proofs. But essentially, it means that the dimension can grow almost exponentially in the sample size. Okay, so in principle, at least sort of in theory, we should be able to learn fairly large trees based on our data. And there's also similar results for trees based on the chi coefficient, but they kind of are similar in spirit, so I'm not really going to go into details for that one. Okay, so that's the type of guarantee that we can obtain on learning extremal tree structures. Now, I do have a couple of simulations. In the interest of time, I will not go through the simulations in a lot of detail, but the one takeaway message from those simulations is that the orange line is recovering minimal spanning trees based on chi, and the green line corresponds to minimal spanning trees based on the combined gamma that I was mentioning before. And the two lines in the middle are two other approaches. And the reason why we invested so much time in concentration bounds and theoretical analysis of gamma is because it performs almost an order of magnitude better than things based on chi. Okay, so that's one thing that we observe here. Although the trees based on chi are also consistent, things based on gamma perform very substantially better. And we observed that across a couple of different simulation settings and across a couple of different models. So it's not that I'm showing you the best picture, it's just that gamma utilizes much more information in the sample than chi. If you look at the definition of those quantities, it's actually a very natural result that one might expect. Okay, and as I say, that is kind of a universal result. Now, the other thing that I'd like to briefly mention is I'd like to very briefly comment on the data application. And essentially, this data application is based on taking foreign exchange rates for 26 currencies relative to the British pound between 2005 and 2010. And then applying an Armagh-Gauge filter to remove seasonality and to remove at least a part of the stochastic volatility, and then applying our methodology to the corresponding filter data. And if you do that, then the picture here is a minimal spanning tree that we get. And one thing that's interesting here is that although we didn't put in any side information about what those data actually are, if you look at the pictures, then we see a couple of interesting things. Okay, and I'd like to point out a couple of them. So first of all, East European countries, namely Hungary, Poland, and Czech Republic, are all very close on this tree. Okay, second, Scandinavian countries, Norway, Sweden, and Denmark are also very close on this tree. And all of them are closely connected to the euro or to the European Union. Okay, another interesting connection is between Switzerland and Japan that puzzled us somewhat when we first saw it, but then it was actually pointed out to us by finance experts that that's very reasonable because both currencies are kind of relatively independent of the world economy and are sort of considered safe haven currencies. So this connection also makes a lot of sense. And then we also have countries from the Commonwealth, so Canada, Australia, New Zealand, and South Africa that are close together. And we have a lot of far East Asian countries like China, Thailand, Korea, India, and so on that are also kind of relatively close. Okay, and so that's what I mean by this type of graph structure learning can be useful for understanding the underlying dependence in the data. Okay, so we didn't put in any of that information, but actually the tree told us that those things are kind of more dependent than, for instance, the currencies of things that are far away, right? So from this tree, we would not see any strong dependence between the currency of Hungary and Saudi Arabia, for instance. Okay, and so in a sense, this tells us something reasonable about the underlying dependence. So it can be used as a tool for exploring the underlying dependence structure of random vectors. Okay, I also have another bit of sanity checks for this model, but actually in the interest of time, I will probably skip that one. I'll be happy to go back to that during the Q&A session. Because for the last 10 minutes or so, I'd like to present a second part, which is learning general graphs for the specific class of Hüsler-Reiss models. And in addition to the concentration bound part, this is really what makes up part of the thesis of Mikhail. So a lot of the things that I'm going to talk about next are actually his work. Okay, so first of all, what are Hüsler-Reiss distributions? Okay, so in general, Hüsler-Reiss distributions can be vaguely seen as a sort of equivalent of the normal distributions in the extremal world. And more precisely, they are defined as follows. Okay, so they are parametrized by a parameter matrix gamma that happens to correspond with the extremal variogram matrix that I introduced a couple of slides earlier. Okay, and so one can show that all those extremal variogram matrices are equal for all values of m, and they are equal to this matrix gamma. Now, those Hüsler-Reiss distributions have a nice stochastic representation, which goes as follows. We take a standard Pareto distribution, and we take a degenerate multivariate normal distribution that's independent of the standard Pareto distribution. Okay, and this multivariate normal has entry 1 almost surely in the m's component, which makes it degenerate. And if we take out the m's component, then that has a covariance matrix of the following form, which is essentially linked to the variogram matrix gamma. Okay. And then we define our random variable y superscript m through Pareto distribution times x of wm minus gamma. Okay, so we simulate this Pareto, we simulate this normal, and then from that we get the distribution of y superscript m. And because Hüsler-Reiss distributions have densities, this Hüsler-Reiss distribution is essentially uniquely determined by this ym for any value of m. And now the interesting thing about Hüsler-Reiss distributions is that similarly to normal distributions, their conditional independence structure is encoded in zeros of a certain matrix that's closely related to this matrix gamma. Okay, so more precisely, if we have a Hüsler-Reiss distribution with parameter matrix gamma, that is a graphical model on an arbitrary connected, I should add, graph G, then that's true if and only if we take the matrix theta m, which is the inverse of this variance covariance matrix sigma m up here, which is a d minus 1 by d minus 1 matrix. And then we add zeros in the m's row and m's column of this matrix to make it a d by d matrix. And then the sparsity pattern of this matrix includes information about the graphical structure of this multivariate Pareto distribution W. So it's kind of similar to the Gaussian world, but there's a slight difference here, which is if either I or j are equal to m, then conditional independence is included not in zeros in the precision matrix, but it's included in zeros in row and column sums. Okay, so if I or j are equal to m, to this m here, then things get slightly more complicated. Which means that from any matrix theta m, we can recover almost all of the graph structure from zeros in that matrix, except for edges that are connected to node m, and there things get more complicated. Okay. And that, of course, now also motivates an algorithm for learning the underlying graph. Okay, so this is just a copy of the result on the previous slide. Okay, now what would we do in practice? Okay, first of all, we estimate our parameter matrix gamma and plug it in to get an estimator of the parameter matrix sigma m. Okay, that's just simple plugin. Now assume that we have any procedure that takes as input sigma m hat and gives us as output theta m hat, which is a sparse estimator of the inverse. Okay, so you could think of things like graphical lasso, neighborhood selection, climb, tiger, whatever your favorite method for doing that is. And then from that, we can get an estimated graph that will have edges in between I and j if the ij's entry of the sort of transformed matrix theta m hat is not equal to 0. Okay, what that will give us is an estimate of the nodes in the underlying graph, except for edges that are connected to m. Okay, but now we can, of course, repeat that for every m. So we get a total of d estimated graphs, and we can combine the information in those graphs by majority voting. Okay, so the final estimated graph for the Hüsler-Reiss distribution is obtained from the original graphs by including all edges that are in at least half of the graphs GM that are informative about the presence of edges between I and j. Okay, so we do this for every m, and then we pool this information together through some kind of majority voting algorithm. And that would be our estimate of the underlying graph structure. Now, actually, the first thing that one might wonder about is whether it isn't more natural to come up with a penalty that penalizes not only entries, but also row sums and column sums. Okay, because that might be a much more straightforward way to obtain a sparse estimator of the graph than doing this majority voting thing. It turns out that that's possible, but kind of, and the naive way of doing this with a Lesop type penalty doesn't work. So that's something that we're currently exploring, but it is more subtle than one might think. So just doing the naive thing turns out to not work in practice. That's one thing that I can say. And then finally, what we also have obtained so far is theoretical guarantees on this algorithm here, recovering the true graph for two particular instances of sparse estimators of the inverse covariance matrix. Okay, and those are the graphical lasso style and the neighborhood selection style. So in 1 minute, what's the graphical lasso style? Okay, graphical lasso was essentially motivated by Gaussian graphical models, where people wanted to take a sample covariance matrix and obtain a sparse estimator of its inverse. And one thing that was proposed there is to take, so imagine for a second that this is a sample covariance matrix from an IID set of normal 0 sigma random vectors. Then this first part here would essentially correspond to the likelihood that one would need to maximize to obtain the corresponding precision matrix theta. And then it's very natural to add a Lasso type penalty, which essentially penalizes the off-diagonal terms of this matrix to force some of them to be 0. Okay, and this was first proposed by Yuan and Lin, and then graphical lasso actually refers to an algorithm by Hasty and Tipchirani that is and I think I might have forgotten somebody here. That is that's an efficient algorithm to solve this computational problem. Okay, now the thing is that although this is motivated from a Gaussian likelihood, and although this is motivated and theoretically studied in the setting where data are multivariate normal, it turns out that there's nothing too special about the multivariate normal. We can plug in any estimator for sigma, and as long as that estimator satisfies certain concentration bounds, this will give us a reasonable estimator of the inverse. And the second, more neighborhood selection style by Mainshausen and Bühlmann, is essentially not trying to solve the problem of estimating the inverse of the matrix all at once, but instead trying to estimate the sparsity pattern of the inverse matrix row by row. And it does so in a form that might not look very familiar here, but that after a bit of computation actually turns out to be exactly equivalent to the classical lasso problem. If we take the m's entry and we regress the m's entry of a vector on all the other entries of that vector. If you do that with a lasso minimization problem, then after a bit of computation, it turns out that that's exactly equivalent to the formulation down here. Okay, so this is really the classical lasso in disguise in a certain sense. And again, it was motivated and studied for multivariate normals, but it turns out that for it to work, all that we need are certain block matrix inversion formula. And that's actually our first type of result that was obtained by Mikhail, which is saying that if, for instance, we do graph recovery with the lasso type approach, which I call Mainshausen-Bühlmann here, as before, Then under a couple of technical assumptions on the underlying matrix sigma hat, we will recover the sparsity pattern in sigma inverse, provided that the subnorm of sigma hat minus sigma is below this bound over here. And this bound has a couple of constants that are related to the underlying matrix sigma. And there's 2 points here that I would to point out. First of all, there's a kind of minimal signal condition. So this is in a sense measuring the value of the smallest non-zero entry relative to the diagonal. This measures how hard it is to separate something that's zero from non-zero. And the second one is this 1 over S here, where S denotes the maximal degree of the graph. So S is the maximal number of connections that any node can have to another node. So if the graph is very sparse, then S would be small. If the graph is very dense, then S would be large. And it's natural to expect that if the graph is very dense, the problem will get very difficult, because then essentially we have a very high dimensional parameter that we need to estimate. Whereas if the graph is sparse, the dimension of the parameter is smaller. Okay, and so this is essentially translating classical results from the analysis of the lasso and the graphical lasso, and just putting them in an abstract framework where we don't use any properties of Gaussian distributions and so on. And combined with the concentration bounds on sigma hat m minus sigma, we can also obtain a guarantee on recovering the true underlying graph. Okay, and so that's the last technical slide that I have. Essentially, we obtain as a corollary a bound of the following form. So this here is essentially taking the concentration inequalities that we had before and turning it into an OP bound for the maximal distance between sigma hat and sigma. And then assuming that a couple of things are constant, we see that as long as this here goes to 0 faster, then 1 over the sparsity times the minimal signal strength, we are guaranteed to get consistent recovery of the underlying graphical structure with probability going to 1. Okay, and again, there's a couple of interesting things here from the perspective of extreme value theory, for example, like the optimal choice of k now depends on our dimension. Okay, so the dimension is allowed to grow. If the dimension grows faster, optimal choice of k changes. And we can also obtain more precise results that give us bounds on the probability, but I just wanted to state something here that looks a bit more tractable than those bounds. Now, the final thing that I would like to very briefly mention, okay, I have a couple of simulations, but let me probably skip over those. So the one thing that we did observe in simulations is that the graphical lasso typically doesn't work all too well for extreme value distributions, whereas Meinshausen-Bühlmann does work a lot better. And the reason seems to be that there are certain kinds of technical incoherence conditions which look like they're just technical conditions, but which can actually be satisfied for one and fail for the other, specifically in the setting where we consider extreme value distributions. That was an interesting discovery for us. And okay, yeah, I'm sorry that the end is a bit rushed. So with that, I think it's about time to wrap up. So in summary, we have started answering a couple of questions, but I would say that there's much more open questions than there's questions that are answered so far. So this seems to be a very exciting direction to continue working on. As I say, there's a lot of things that we still don't know. And I'm sure that Mikhail will answer many of those because he's something who is a really wonderful guy to work on the stuff. So I'm sure that you'll see a lot of very good work from him going forward in those directions. Okay, and so that's all that I had to say. Thanks a lot for being here and for listening to me for so long.
Okay, thank you very much, Stanislav. Floor is open for questions. So please, if you have questions, turn on your mic and if possible, your camera so that we can see you. If I don't see you, please just go ahead with your question because I don't see the list of the people. Okay, I guess I have a couple of questions if people are shy to ask questions. I actually had question on the choice of K, and then I noticed that you have it on the list at the bottom of the future work. So what you do currently in the simulation and real data,
okay, so
you select it as a tuning parameter, or?
Yes, so in the simulations, we actually have several types of simulations. So one simulation is looking at the performance of the method as a function of K.
Mm-hmm.
And then, well, a typical plot of this style of simulation looks somewhat like this. So if this is K, then, and we have some performance metric, then sort of typical plots look like this. Of course, there's an optimal value of K.
Mm-hmm.
And the difficulty kind of is that this optimal value of K depends on the underlying setting and the underlying model and all kinds of things.
Mm-hmm.
And the second difficulty is that from the theory, we see that the optimal choice of K is not necessarily driven by a bias variance trade-off in the classical sense. So a lot of the classical plug-in estimators with estimating a second order bias and then plugging something in actually don't really work in our setting. So for data analysis, and another classical way to choose K that's kind of not very automatic, but that I think people do in practice, is they run their estimators for a couple of different values of K, and then they look for some kind of stable regions. Okay, so if there's a range of values of K where all the estimators are roughly similar, that's a good indication that might be a reasonable choice for K. And essentially, that's, I think, for now, what we would suggest to use in practice. Now, of course, for estimating a graph, even coming up with a sensible notion of what stable means is a bit less clear than it is for parameter estimation. And so right now, for instance, we are exploring things like plotting how much the graph changes on a grid of K relative to the previous value of K. And the hope essentially is that if there's a lot of change in a region for K, then that's not a good estimator, while if there's a region where it doesn't change a whole lot, that would be our stable region in the sense of a classical type of hill plot. Yeah,
and that would be a range of Ks, right? That could result in.
Yeah, and then one would essentially, the hope would be that whatever K we pick in that range, the answer that we get doesn't depend on the very specific value of K in that range. Right, so if the graph is relatively stable, then whatever K we pick in that range, we would get a graph that looks fairly similar. And so, for instance, in terms of interpretation, the interpretation wouldn't change that much.
Shall I continue with my questions, or there are questions from audience?
Okay, I have a question.
Yes,
okay,
please.
Yeah. Hello, my name is Arush. So my question is, so to estimate the graphical structure for this extremal type of data, the one approach, but let's say there was some other kind of complications, such as incomplete data, like censored data. Then what? So like here I see it's very focused on this extreme value theory, this variogram, and what would be this kind of approach? I don't know, it may be not fair to ask.
Well, so I mean, in general, I think that this general idea of sort of a plug-in principle is of course also applicable to different types of data. So for instance, if we assume that our data are Gaussian, but that they're smithing data, then essentially to estimate a Gaussian graphical model, what we really need is a reasonable estimator in the sense of convergence rates of the covariance matrix. And then we can plug that covariance matrix estimator into this inversion, and then from that we can estimate the graphical structure. So essentially it would really boil down to taking proper measures to account for missing data to get consistent estimators of covariances. And if that's possible, then I think from there one would probably follow the usual route. Now for trees, I would guess that it might be more difficult taking this route through sort of non-parametric density estimation and mutual information, because I guess with missing data, and especially with sensor data, estimating densities on the whole domain might be difficult.
Okay.
But there again, I mean, either one, if one has an idea about the data, then one could assume a specific parametric model, and then again, estimate parameters in that model. And based on that mutual information from those parameters, essentially use a plugin type of estimator to minimal spanning tree. Yeah, so I guess sort of the key is finding parameters that can be estimated under the particular type of missingness or censoring or incompleteness of the data that one observes.
Okay.
And if that's feasible, then the downstream analysis is essentially sort of should follow from high-level results on if you get a reasonable estimator in the first step, then that kind of propagates to reasonable estimator in the final step.
Thank you.
More questions? Okay, then I go ahead with my question. So if the sparsity is not of a concern, but we just want to get a stable estimate of the graph, like related to graphical lasso, instead of using graphical lasso for theta hat, we could do a ridge type estimator.
Yes, but I think so. The difficulty is that sort of sparsity is linked to the graph. So if you do a ridge type estimator, then we would get a stable estimator of the precision matrix.
But you get all edges all over the place, I guess.
Yeah, but there would be no zeros in there. So I guess one could do ridge plus some kind of thresholding.
Like a convex combination of a ridge and something else. Okay.
Yeah, or yeah, one could either do sort of this elastic net, so like a partial ridge and a partial lasso penalty to get additional stability in estimating the precision matrix. But then to get something really sparse with, for instance, just the ridge, I guess one would probably really need to do some kind of second stage thresholding. But that might also be feasible, right? So we first estimate something and then we do some kind of testing for each of those entries as 0 or non-zero.
So speaking about testing, would you be able to do any inference on the estimated graph?
Yeah, so that is actually, I guess, one of the other open questions in a sense for now. How do we? Yeah, so it would be really nice, I think, to be able to say, like, for instance, get the confidence set for the edges of the minimal spanning tree. But that would be also linked to sort of going beyond concentration, unless we are fine with something that's really very sort of conservative and really understanding asymptotic distributions. And that's actually also part of what we are doing right now. So we are deriving the limiting distribution of this estimated variogram. And then from there, I believe that eventually it should be possible to get some kind of confidence statements about the edge set, and for instance, or testing for whether this particular edge is present or not.
That could be related to what people call it post-selection inference. I think in the context of graphical lasso, you select and then you want to do certain inference.
Yeah, right. So the difficulty there would, of course, be that we use the same data for selecting and for inference. And then, so for the graphical lasso specifically, I believe, and there are, so at least for the classical lasso, there's this debiased lasso, for instance, where one can do inference. And I would guess that those ideas could be carried over to the extremes world after some amount of work in a similar fashion, probably. In general, that would be very interesting. And I think that even in the non-extreme world, there is some work on that, but it's not that there's a huge amount of work specifically, because it's also a difficult question, I guess. But it's a very important question for sure.
Okay. Questions from audience? Okay. I guess I'm going to stay. So let's thank our speaker one more time. Thank you very much. I'm going to stay anyway. So if people want to leave in case it's Friday afternoon.
Yeah, I guess Friday is always a especially by Friday afternoon. Everybody is
Yeah.
just tired as well.